Hello students, this is Nikhil Churi, your instructor for Business Stats 2 for the fall 2023 semester. Getting started with our very first lecture, chapter number 10, Statistical Inference Concerning Two Populations. So like I said in our syllabus video, we will be continuing with whatever we learn in our Business Stats 1, like the hypothesis testing, interval estimation, a part of sampling, distribution, and so on. So this is the continuation. A brief overview of what we will be learning in this lecture, in this class topic. Subtopic 10.1, subtopic 10.2, and 10.3. So in 10.1, we'll be learning about how to make inferences about the difference between two population means based on independent sampling. So again, I want you guys to understand two things over here. The first one is two population means. So somewhere there are like two different populations, say heights of people in California versus height of people in New York. So again, that's an example of two different populations. Same is like say height of trees in say Idaho versus height of trees in somewhere in say Rhode Islands, or maybe in two different countries. So these are two different populations, and there can be number of data points. And again, I'm talking about population, so that means that I'm talking about each and every data point. So yeah, that's one thing. So there will be two different populations, and the second part is independent sampling. So there is something called as independent sampling that we'll be learning about as we go. 10.2 is about making inferences about the mean differences based on matched pair samples. So again, there is some theory over here about matched pair samples we'll be learning. 10.3 will be making inferences about the difference between two population proportions based on independent sampling. So again, in all these three statements, the two population is common. So first one is two population means. Second one is two population, but again, we are looking at the mean differences. And third one is two population proportions. Yeah, so we'll be discussing about something about proportions. And again, I have like specifically mentioned which slides are dealing with which. So 10.1 we'll be learning about from slide 3 to 29. For 10.2 we'll be learning from slide 30 to 41, and the last one we'll be learning from slide 42 to 52. And again, in each of these segments of slides, I think last 4, 5, or 6 number of slides are based on numerical problems. And these are the exact type of numerical problems you'll be having for your online homework assignments in McGraw-Hill. So yeah, please pay attention on those problems as well. Moving forward, let's read this introductory case. And again, this is introductory case is nothing but an example we'll be using while learning the theory as well as solving the problem. So I'll just read it out over here what the problem is. So in the year, in the month March 2010, federal healthcare law required chain restaurants with 20 locations or more to post calorific information on their menus. Yeah, so I think it's clear. So this rule is coming from federal law requiring chain restaurants to mention the calorific information. So suppose there is one menu item 1, these are the calories, menu item 2, and so on. Second is this would make it easier for consumers to select healthier food options. Nutritionist. So there is this nutritionist, Molly Hostler, would like to study the effects of a recent local menu ordinance requiring calorific posting in San Mateo, California. So she obtains transaction data for 40 Starbucks card holder around the time that San Mateo implemented this ordinance. Yeah, something more continuation. So here is the sample data. So yeah, again in the very first column you can see customer number 1 to 40 is mentioned. So again, the very first thing you can clearly see that the number of data points is 40. So yeah, here your n is 40. And in the next column, it says drink calories, and before the ordinance, these were the drink calories that a customer purchased. Yeah, customer 1, 2, 3, 4, 5, 6 until 40 purchased. And in the second column, it says drink calories after. So after the ordinance was put into place, it was implemented. These are the calories listed. And the next column talks about food calories before the ordinance. And the next column, last column, talks about full calories after the ordinance. Yeah. And just again, this is, yeah, I'll say partial data showed over here, just explaining the structure of the data that has been collected. And I'll be posting this Excel sheet also where all the details are given. Yeah. So again, that data that we are seeing, yeah, before and after, and this is Starbucks. So yeah, the drinks calories are posted over here. So yeah, 1 to 40 data points are given, and again all the details are given over here. So first one being 141, 137, 144, 149, 149, 152, so on and on and on until the last one, which is 147. Same is the case with after. Yeah, so all this data before and after is given. Similar is the case for food calories. So yeah, before and after, first one being 395, 404, 401, 405, 396, so on until the last one being 406. And same is the case with after, which is 378, 392, 395 until all the way it is 400. Yeah, so this is for food. So the very first we saw was for your drinks. Before and after the ordinance, the law was put into place. The second one being for the food, before and after. And again, the reason I'm saying is like in statistical analysis, or just not only for the scope of this class where you'll be solving problem, analyzing this type of data all the time, but even in, like, suppose you graduate, go to job, you will be given these types of data. Yeah. So it's always good to quickly familiarize, look at the structure of the data, of the sheet, the data that has been given to you, identify what you are looking at. In this case, we saw there are like before and after, total 40 data points each. And again, as you go, as you use more and more of these principles, oftentimes you might be dealing with data points which are not equal. So maybe, yeah. So what I'm saying is, like, in this case, the first data set has 40 points. The second data points might have 50, 60, 100. So those numbers might not be matching. It's totally okay. Yeah. So yeah, so now right now what we are doing is we are familiarizing ourselves with what data is given. So yeah, we saw those. And what's this? So this is something else. Yeah, we'll come back later. So these are the two sheets we are looking at. Yeah. So going back to our PowerPoint presentation. So yeah, we saw the Excel sheet and each and every data point that that has been collected. So based on all this information collected, Molly wants to use the sample information to, number one, determine whether average calories of purchased drinks declined after passage of the ordinance. Yeah, so that's the first question here. She want to see if posting the information, did average calories decline or not. Yeah, so that's the first information she wants to determine. Second is she wants to determine whether average calories of food purchased declined after passage of the ordinance. So yeah, same like similar to drinks calorie before and after, she want to know if the average calorie declined after the ordinance was passed. And lastly, she wants to access the implications of caloric postings for Starbucks and other food chain. Yeah. So these are the three main piece of information she is trying to collect and know based on the data that has been collected. And again, that's the power of statistics. So yeah, if you check the overall problem again, so this law was passed, and suppose all the restaurant chains implemented this, and again, based on just one location in San Mateo, data was collected. Now she wants to know, based on this, whether there is a significant difference, yes or no. Yeah. So based on these sample data collected, she wants to make a global inference conclusion whether or not this made a big impact on the calorific consumption patterns of the customer for drinks as well as the food calorie. Yeah, so that's the power of statistics. Using some theories, we are going to use this limited data to make some kind of global inferences, conclusions about the effect of the ordinance that was passed. Yeah, so let's continue with some more theory, and we'll get back to the details as we move on with the theories. Yeah, the next slide, let's learn. And this is more of a revision. So we have learned this independent random sample in business stats 1, and I think there are multiple chapters where we learned it. So yeah, by definition, independent random sample is nothing but it's when two or more random samples are considered independent if the process that generates one sample is completely separate from the process that generates the other sample. Yeah, so there is no commonality. It's completely like collected independently. So suppose, yeah, if I take example of this, so before the data is collected, right? And again, all the details are shown in this Excel sheet over here, and here is the drink calorie. So before, yeah, when the 40 customers were, yeah, so the calorie pick information for all the before customers were collected. Yeah, like not much details are given. So it was, so let's assume maybe the business time for this Starbucks store is, yeah, it's suppose it starts at 6 a.m. and it closes at say 6 p.m. So between those 12-hour cycle, 40 data points were collected. And again, there was no, and suppose the first data was at 6 o'clock, 7 o'clock, 8, 9, 10, and so on. And yeah, every time, or maybe during rush hours, business hours, more data points were collected and so on. So again, same independent approach was used while collecting the after also. So again, there was no commonality. The data collected was completely random. So that's what it means over here. Independent random sampling. So there is no overlapping information between the data collected during these sample data collection. So yeah, this is yeah, something more. The samples are clearly delineated, meaning there is no collinear relation. It's completely independent. And suppose say mu1 is the mean of the first population and mu2 is the mean of second population. Yeah. So again, the challenge over here, and again, mu1 and mu2 can only be assumed. We cannot definitely certify, or yeah, yeah, we can't completely calculate, because yeah, population is like everything. So maybe this data was collected on one day only, but again, the store is going to continue selling the information. Yeah, so sorry, is selling the drinks forever, and all the information cannot be collected for each and every customer that gets. Yeah, so just as a random sampling, 40 different customers before and after were considered. So now, the statistical theories, as per the statistical theories, let's assume mu1 is the mean of all the first population, that is before, and mu2 is the mean of second population after. Yeah, so for now, yeah, just don't think too much about these mu1, mu2. As we go, as we use it more and more, we'll get completely familiarized with the concept of mu1 and mu2. But yeah, let's say mu1 is the mean of first population, mu2 is the mean of second population. Moving forward, confidence interval. Yeah. So again, this is a carry forward of the info, like all the concepts that we have learned in the business stats one. So confidence interval is nothing but it's a range. Yeah. So as per the theory, say confidence interval for the differences between the two means, which is mu1 and mu2. Say, yeah, let's say x1 bar and x2 bar is a point estimator for mu1 and mu2. So what this means is, suppose, let's say the differences between x1 bar, x2 bar. So you guys, if you guys still remember, mu1 and mu2 is nothing but the differences in the averages or the mean values of entire population for these two populations before and after, versus x1 bar and x2 bar. So whenever these letters, X, Y, Z come into picture, it denotes, or what it means is you are dealing with, or you're talking about the sample information. Versus whenever you're using Greek letters or Greek alphabets like mu, sigma, sigma square, and so on, it refers to the entire population. So that's what it means. So let's, since finding the differences or finding the actual values of the entire population is impossible in business world, we are making an assumption that the differences between x1 bar, x2 bar, meaning averages of this before data and averages of this after data, x1 bar, x2 bar, is a true or a good estimator for the differences between the population data for before and after. Yeah, so that's what it means. The value of the sample mean x1 bar minus x2 bar are computed from these two independent random samples with n1 and n2 observations. Yeah. So in this case, we already know our n1 is 40 because we have 40 different data points, and same n2 is also equal. 40 different data points have been collected. So yeah, that's what it means. Next, sampling distribution for x1 bar minus x2 bar is assumed to be normally distributed. So that's a statistical assumption. A linear combination of normally distributed random variable is also normally distributed. Yeah, so that's as per theory we learned in our distribution, normal distribution in business stats 1. And suppose if realistically, even if you do a lot of data collection verification, you find that the x1 bar, x2 bar, they are not normally distributed, or the differences between them is also not normally distributed. Then thanks to the central limit theorem, central limit theorem that we learned in business stats 1. So as per that theory, as long as your number of data points collected is greater than or equal to 30, then blindly you can say that you are applying the central limit theorem. That's as per theory. So as long as your the sample size n is greater than or equal to 30, you are good. So in this case, we have 40 data points. So definitely we can say the central limit theorem applies, and you can apply all the already distributed principles over here. Yeah, so this is what the last line says. So if underlying distribution is not normal, then by the central limit theorem, the sampling distribution of the difference between these two means is approximately normal if both n1 and n2 are greater than or equal to 30. So in this case, that's true. So yeah, thanks to the central limit theorem. Moving forward, so beyond this, it gives rise to three more different scenarios. The first one being, if we know that sigma 1 square and sigma 2 square, then use the z distribution. So again, like I will repeat myself, if you are using Greek letters, Greek alphabet, so in this case it's sigma, meaning I'm talking about the entire population for population 1, and sigma 2 square is for population 2. And uh, mu is a term that you use for averages for the population, and x or x bar is the term that you use for averages of the sample. So similarly, sigma is, or say sigma 1 is a term that you use for the standard deviation of the population 1, and sigma 2 for the standard deviation of population 2. And same, if I'm looking for standard deviation for sample 1, I'll be terming it as S. Yeah, so it will be S1 and S2 if I'm talking about the standard deviation. And if I square that up, yeah, if I square the sigma, so sigma is my standard deviation. And if I square, which is this case, so if I do sigma 1 square, I'm talking about the variance. Yeah. So variance for population 1 is denoted by sigma 1 square, and variance for population 2 is denoted by a sigma 2 square. Then, and again, if these two terms, so the variances for these two terms are given or known, then we use the z distribution to solve the problem. Second scenario, if we do not know the variances for population of population 1 and variances population 2, but we can assume that they are equal, then we use the t distribution, which we'll be learning about as we go in this lecture, with a pooled estimate for variance s square p. Yeah. So again, s, since it's talking about s, so it's a actual English letter, right? English alphabet s. So I know it's we are talking about the sample, and sp square is nothing but there is a formula for it, which I'll be sharing as we go. Then, and the third scenario is if we do not know sigma 1 square, meaning the variance for population 1 and variance for population 2, but we cannot assume that they are equal, then we use the TDF distribution with S1 square, meaning variance for sample 1, and S2 square, which is variance for sample 2. So let's learn a little bit more about all these three scenarios as we move forward. Yeah. So next slide. Yeah. So we are looking at the first scenario, that is the variance for population 1 and variance for population 2 are known, then we use the z distribution table. Yeah, so in that case, this formula applies. So yeah, this is the one. So if sigma 1 square and sigma 2 square are known, meaning the variance for population 1 and variance population 2 are known, then and 100 multiplied by 1 minus alpha percentage of confidence interval of the difference between two population means is mu1 minus mu2 is given by this formula over here. So in this case, I'll just take a maybe 10-20 seconds and talk about this. So in this case, I'm sure you guys still remember what alpha is, what the level of significance is. If not, do not worry. We'll be talking about it shortly. So yeah, in the first scenario, this is the formula you are supposed to use. And again, I'll say sometimes if you try reading a statistical problem, and that too like as advanced as this, it's very easy for you to get lost or get confused or get maybe scared that, okay, this is very difficult. The easiest way or the easiest approach I will highly recommend that you all take is just look at the formula. Yeah. So again, for the first case, this is the formula I'm looking at. Do not think a lot about anything else. Just look at this formula and look at the details. Yeah. So in this formula comprises of, there is a bracket term that's called x1 bar minus x2 bar, meaning this is nothing but, since the English letter is involved, x1 bar meaning it's talking about the sample population. So in this case, average of all this is my x1 bar, and average of the second after x2, like second data set, is my x2 bar. So I'll get the difference. I will calculate the average of, calculate the average of this whole set, and then for x2 bar I'll calculate the average of these two and plug in these numbers. Yeah, so this part is clear. Followed by, there is plus or minus. So again, since there is plus or minus, I definitely know that I'm going to get a range of number. Yeah, so my goal is to find the range. So again, yeah, so, and that range of number will be my confidence interval. Yeah, so there will be one smaller side and there is higher side. So that's my goal to, yeah, to find out. So yeah, plus or minus z alpha by 2. Again, alpha, like I said, it's the level of significance. We'll be talking about it shortly. And z, whenever there is a z value or t value in any formula, remember that you will be getting it from a standard table, yeah, which I'll be talking shortly when we solve the problems. So z at alpha by 2 can be calculated or can be found using a standard distribution table. And then there is a square root term, and within the square root term there is sigma 1 square. So since it's a Greek alphabet, I know I'm talking about the variance for the entire population 1 divided by n1. So I know the total data points are 40 here. My n1 is 40. Second one is sigma 2 square. So it's variance for the entire population for data set 2. And my n2 is 40 over here. Yeah. And again, this is a case where sigma 1 and sigma 1 square and sigma 2 square are known. So if you look at the entire formula, I know where to get this x1 bar, average of these, x2 bar, average of these. Z can be found out from the table as long as I know my alpha level. And since sigma 1 square, sigma 2 square are known, meaning it will be given in the problem. N1 and 2 are known. So technically, I have all the entities required in this formula. So again, once I know what those numbers are, all I have to do is plug in those numbers, get the answer, and you get the confidence interval. Yeah. So one big step completed. Yeah. So that's how you solve these kind of problems. Next, yeah. So scenario number 2, whether yeah, sigma 1 square and sigma 2 square, meaning the variance for population 1 and variance for population 2 are unknown, but assumed to be equal. So again, when I say assumed to be equal, if I get a difference out of them, it will be 0. So yeah, this is the theory you'll be using, and this is the formula you'll be using. Yeah. So they are assumed, but they are unknown, but they are assumed to be equal. So 100 multiplied by 1 minus alpha, again, a level of significance, confidence interval. So this is the range you're trying to find out of the difference between the two population means mu1 and mu2 is given by this formula over here. Yeah. So again, like I said, do not think too much. You'll get confused. Just look at this formula, and this is the formula you'll be using to solve the problem. So again, in this formula, just like previous case, I know x1 bar, x2 bar, averages of each of these, t at alpha by 2 at a given degrees of freedom, and I'll talk about degrees of freedom over here. Yeah. So like at alpha by 2, yeah. So degrees of freedom is nothing but, yeah, the formula for it is n1 plus n2 minus 2. Yeah. So in this case, my n1 is 40 data points. N2 is also 40 data points. So 40 plus 40 minus 2, which gives me 78. Yeah. So my degrees of freedom is 78. So once I know that d of f versus, and once I know my alpha, say 5%, 10%, or 0.5% or 0.1%, and so on, I will refer the standard t table and get this value. And then my next is yeah, this square root term. So the first term is sp square. Yeah. So it's formula for this sp square is given by this formula over here. So just plug in, and within this formula, I know my n1 is 40 here. My s1 square can be is nothing but the variance for the first set of data, meaning here, and yeah, and my s2 square is the variance for this second data set. So I know n1, I know s1 square, I know n2, I know s2 square, I know n1 plus n2. So I'll plug in those numbers and I'll get the sp square value. And that's the value I'll plug in over here. So I know how to find the sp square. Then the next two terms are in the bracket 1 upon n1, which is known 40 n1, and 1 upon n2, which is also known 40. So technically, I have all the entities. I know all the entities that goes into this formula. I'll just plug in and get the values, and I'll get a range of numbers. Yeah, one minimum and one maximum. And again, For the second scenario also, a big step is completed. Yeah, now let's go to the third one, which is if sigma 1 square and sigma 2 square, meaning my variance for population 1 and variance for population 2 are unknown but cannot be assumed equal. 100 multiplied by 1 minus alpha percent confidence interval of the difference between the two population mean alpha 1 and alpha 2 is given by, yeah, just look at the formula. Do not think too much. Just look at the formula. So similar to the previous two formulas, I know my x1 bar, my x2 bar, averages of each of these, t at alpha by 2 at degrees of freedom. Here also degrees of freedom the same, n1 plus n2 minus 2. So once I know, well, alpha is usually given in the problem. When I see 95%, my alpha is 5%. Yeah, so yeah, for t at 5 upon 2, which is 2.5, and yeah, degrees of freedom, that is n1 plus n2 minus 2. I know these, so I can find out t divided, multiplied by square root of s1 square, meaning the variance for first data set divided by n1, which is 40, plus variance for second data set divided by n2, which is 40. Yeah, and hey, so one more difference here is for the third scenario, the degrees of there is a different formula for d of f, which looks complicated, but again, for each and every entity over here can be calculated. So s1 square coming from this, n1 is 40, s2 square coming from this, n2 is 40, and just plugging these numbers. Hey, this formula looks complicated. If you guys want, well, again, it's all about statistical theories. If you guys still want, you guys can still use this d of f of n1 plus n2 minus 2 over here also. I'll tell you a secret. I'll tell you the reason why is that, well, using this formula, you'll get a number. And I can confidently tell you that the number that you will be getting using this formula will be very close to this. Yeah, so that's the reason I'm openly telling you guys, go ahead and use the same formula for d of f, which is a simplified version, that is n1 plus n2 minus 2, and you should be fine. Or else, if you are very good at using excel, yeah, feel free to use this one. But yeah, again, I won't be deducting points from your homework or your exam if you use either this simplified version or this complicated version. Yeah. So yeah, this is your third scenario. So in each of these scenario, just remember, this is more of a refresher. Just remember, don't overthink too much about what these terms are. Eventually, as you use it while solving your problems, you will get used to it. And in the longer run at your work, once you start using it more and more, you'll completely, you'll find that it's very, very easy, straightforward. But yeah, just focus on the formulas. So for first case, this is your formula to calculate the confidence interval. For second scenario, this is your formula, and third scenario, this is your formula. Yeah, and again, and each of these formulas, your job is to, or your goal is to identify each and every of this entity. And usually the answer is, I mean, it's x1 bar, x2 bar is either given in the problem itself, or a data set like this is given, and you can always measure those values, or calculate these values from the data set. Yeah. So for example, I'm taking a pause over here, and let's discuss a bit more of this formula in the reference to the first data set that is given. Hey guys, first thing I want you guys to do is open your Excel and go into your data tab over here. You can see this, right? The data tab. And within this data tab, if you go to the extreme right hand side, you must see a data analysis tab over here. Yeah. And now again, there are two things. One is like, again, this data analysis tab doesn't come by default if you haven't activated it already. Well, it's there in your Excel, but you have to activate it. And since I've activated it like long time ago, I'm seeing this. If you're not seeing this, again, I'll repeat, open your Excel, go to your data tab over here. I'm clicking, and in the data tab, if I go to extreme right hand side, I must see this data analysis tab. If you're not seeing it, here is a way to activate it. Yeah. So if you're not seeing this data analysis in your data tab, go to file, and within this file, you will see a screen like this. On your extreme left hand side bar, go to all the way to the bottom, and where you can see this options. So click on the options. A window like this will pop up, and within this, go all the way to the second last where it says add ins. Click on that, and once you click on that, a screen like this will appear, and within this, I'm seeing this analysis tool pack. Yeah. Well, since I've activated it, it's there on my top row. For you guys, maybe it will be here or maybe it will be somewhere over here. Again, there are not a lot of them, so it should be very easy for you to find. So if you're not seeing it in the second tab, scroll through here and yeah, you must see analysis toolback. Well, this is for VBA. I'm not looking for VBA. We are looking for this simple, straightforward Excel version only. So click on analysis toolpack, and for you, yeah, make sure here it says manage Excel add-ins and click go. Yeah, click go and then click OK. You must see that tab over here. Yeah. So again, I select yeah, over here I'm checking this and saying OK, and it must appear in your yeah upper tab over here. Yeah. Yeah, that's how you activate it. And again, I don't think we'll be using this today, but as we go, this is a very useful bar, and we'll be using this a lot in our chi-square as well as ANOVA, and very much during our regression. That makes your life very easy. So anyways, coming back, yeah. So again, I will go over here. So coming back to our first scenario, and again, these are the two data points, sorry, data sets given for drinks, as well as here two data sets for food calories. Yeah, so focusing on the drinks. Yeah, so we know there are 40 data points collected, and these are the values of each and every data point for each of this before and after. So if I have to calculate x1 bar, yeah, do not take your calculator. I mean, if you want, feel free. But again, I'll tell you some easy tricks in Excel. I can do this using analysis tab also, but for now I'll hold off. Let's follow this standard procedure. So to get the x1 bar, if you guys, I'm sure many of you already know. If you don't know, here is the way you do it. So I'm going to this tab A43. I'm leaving one tab in between. Go to tab A43, and I'm typing equals to. I will say AVERAGE of, so average. Yeah, I'm typing AVERAGE, and then starting a bracket, and then what I'm doing is I'm selecting all the points from A2 until A41. I'm closing the tab. You see this, right? I'm closing the tab and I'm clicking enter. Yeah, once I do that, I will get all the averages. Sorry, I'll get the average for the first data set. Yeah, I will do the same for B as well. Okay, before that, maybe I'll just arrange this data. And this is just me. I like my data to be well arranged, well presentable. Bold, and again it's a good practice. I will highly recommend you guys also sorry, to get used to this practice of making your data look very systematic, very organized. So yeah, I did for the first one, which is equals to average of A2 to A41. I'll do the same thing for B as well. Yeah, so you see what I'm typing here. Yeah, equals to AVERAGE bracket start, selecting all the way all these data points and closing it. Yeah, so I get the average for second one also. Yeah, so again, maybe on the third C 43, I will say equals. So these are nothing but my averages. Oh no, sorry. Since I'm using equalistic, it's creating a formula which I don't want. I'll just say average, or this is my mean for the sample. Yeah, so this is what I got. So coming back to our, oops, I did a mistake. Sorry. Okay, coming back to our PowerPoint slides. Yeah, so I found this is my x1 bar. This is my x2 bar. Z will get there. Sigma 1 square. In this case, sigma 1 and sigma 2 are already given, known, right? So it should be given in the problem. So do not worry. My N1 and N2 are 40 here, so I don't have to worry. Let's go to the second case. Yeah. In this case, there is one more added term, SP square, and within the SP square, the formula for SP square is given by N1 minus 1 multiplied by S1 square. So let's see how to calculate this S1 square and S2 square. Yeah. Once you know, I think you already know N1, N2, N1, N2. So the only unknown is S1 square as S2 square. Yeah. So this S1 square and S2 square are nothing but the variances for sample. Yeah. So sample, VARIANCE. Yeah. You see, well, yeah, I think my screen. Yeah, here it is. So this is my sample variance. So how to calculate the S1 square and S2 square? Very straightforward in Excel. See, what I did is I started in this cell A A44. So I'm going there, I'm typing equals to, and look at the command I'm using. Yeah, so var is the command I'll use. In this case, it's var.s, but do not worry, just see what I'm doing. So I'm typing var, starting a bracket and selecting the exact same data points which I used for x1 bar and closing the bracket. Yeah, so you see what I did here. I typed equals to var, bracket start, selected A2 to A41. I closed the bracket and now I'm pressing enter. So I got 34.25. Yeah? So that's my S1 square. I do the same for S2 square also. So I'm starting with equals to var, start a bracket, go back here, select the same data points for after, that is B row, and I got the value of 32.33. So that's my variance for data 2. So that's my S2 square. So once I know these, I can find out SP square because I already know the other entities. So I just plug in the number, I will get SP square. I plug in this number SP square over here. And yeah, you'll be able to calculate your confidence interval. Yeah, in second case as well as the, I think, third case as well, right? I mean, you have S1 square, S2 square. So this is how you calculate the S1 square, S2 square. How to calculate the z value at alpha by 2 or the t value at alpha by 2 at and given degrees of freedom. Very straightforward. Let's go to a problem on slide number. Hey, sorry, I take my words back. Let's go to the next slide and have a refresher about what a hypothesis test is. And again, this whole topic was covered during one of our topic hypothesis testing in Business Stats 1, that is 2340. So there was a whole chapter dedicated for hypothesis testing. So as a refresher, I just pulled one, or I think, yeah, the next 2 or 3 slides. So what a hypothesis test for mu1 minus mu2 is when conducting hypothesis test concerning the differences between the two population mean mu1 and mu2, the competing hypothesis will take one of the following 3 forms. Yeah. So if you guys still remember what a two-tail test is, right? Like one tail, and within one tail test, there are two, which is right tail or left tail. So everything is about the either one of these 3 tests. Yeah. So the two-tail test is denoted by HO, which is your null hypothesis, is mu1 minus mu2 equals to some difference d0, and with that, by default, you're conflicting or contradicting test HA. Yeah, so null hypothesis and contradictory to null hypothesis is your HA, alternative hypothesis, is mu1 minus mu2 is not equal to d0. Yeah, so your null hypothesis says equal to, and if it says equal to, your contradictory HA is not equal to d0. So that's how the first case is. Second is right tail test. So with that theory, it says that your null hypothesis mu1 minus mu2 is less than or equal to d0. With that logic, that theory, your alternative or contradictory hypothesis says mu1 minus mu2 is opposite of this, meaning greater than d0. Yeah. Third one, left tail, is HO states that mu1 minus mu2 is greater than equal to d0. With that logic, the contradictory case is mu1 minus mu2 is less than d0. So now let's check few more theories about these 3 cases. Just remember all your equality sign. Yeah, you see this here, it says equal to, here it says less than or equal to, here it says right than or greater than or equal to. So the equality sign is always present in your HO or null hypothesis. There is no equality sign in your alternative. Yeah. So here it says not equal to, meaning there is no equality sign. Second case, it says, I mean, there is nothing. So it only says a straightforward greater than. Yeah. Third is less than, but again, in all these HA, there is no equality sign. So that's a property characteristic of these hypothesis test, all these 3. Second is your tail. Yeah, your two tail or right tail or left tail is always identified using your HA. Yeah. So again, you can see HA says not equal to. So you write equal to sign and cross it out. So not equal to. So there are two tails, right? Yeah. Let's call each of this whatever endpoint as a tail. So there are two tailed over here. So that's why it's two tailed. Similarly, your right hand side. Yeah. So your HA says greater than, right? So you can see this point over here. Let's say this is a tail. So this is pointing my right. So that's why it's right tailed. Similarly, for your left tail test, it says less than, right? So let's say this is your tail. So yeah, this point is on your left. So that's why it's left tailed. So yeah. So that's what it means. So this is a refresher for hypothesis test. So these are the three conditions you'll be looking at while solving any problem. And we'll talk about it later. And like I said, this hypothesis test, initially it sound confusing. Do not worry a lot. Let's let's try your best to understand or grasp it as much as we can. And when we solve the problem, meaning we'll be learning by doing. When we solve the problem, we will clarify some more things about the same. And believe me, you guys will get it, what it is. So moving forward, yeah. So this is the basic for hypothesis testing. Moving forward, a test statistic for testing the difference between the two population mean when the sampling distribution for x1 bar minus x2 bar is normal. Yeah. So assuming x1 minus x2 bar, meaning your sample differences, right? First data set sample, second data set is normal. And in this case, you can definitely do it because it's 40. So with that logic, the z, calculating z is calculation of z is done by this formula. So again, x1 bar minus x2 bar, again, your x1 bar is 142 in this case, 140 in this case. And that difference d0, usually it's not given. Yeah. And if it is not given, straightforward, assume it to be 0. So technically you are looking at z equals to x1 bar minus x2 bar minus 0 divided by square root of sigma 1 square plus sigma square upon n1 plus sigma 2 square upon n2. Here also x1 bar, x2 bar, n1 and n2 can be found out here. And since the first case sigma 1 square and sigma 2 square are known, you can calculate the z. Next, scenario 2, if sigma square and sigma 2 square, meaning the population variances for data 1, population variance for data 2 are unknown but assume equal, then the test statistic is assumed to follow the t distribution table or TDF, and its value is calculated using this formula. So again, TDF equals to x1 bar minus x2 bar minus d0. If not given, straightforward, assume the d0 to be 0, divided by square root of sp square multiplied by 1 upon n plus 1 upon n2. And again, formula for sp is already given over here. And again, for sp, all you need to know is the number of data points n1, n2, and s1, s2 can be calculated using Excel. Yeah, so just plug in that number, you know n1, you know n2, and here, yeah, the same formula is sp square. And degrees of freedom d of f is n1 plus n2 minus 2. And similarly, the third one, yeah, that is the population variance for population variance for data 2 are unknown and cannot be assumed equal. That the test statistic is assumed to follow the t distribution formula for TDF. Again, similar, x1 bar minus x2 bar minus d0. If not given, this is 0 divided by square root of square root of this entity s1 square divided by n1 plus s2 square divided by n2. And yeah, formula for d of f is given by here. And here also I'll give you the luxury, if you guys want to use a simple formula for d of f, that is n1 plus n2 minus 2, I'll still give you the points. Moving forward, yeah. So problem. Well, hey, so these are the problems that were coming from the textbook PowerPoint only. I think a better solution for you, that is, yeah, let's directly jump to slide number 25, I will say. And again, the reason is, I think, yeah, these problems cover everything that is required for you guys to understand as a part of this class, as well as your homework problems are very similar to these. Yeah. So let's look at the first problem. So again, in this problem, this data is given. So consider the following data. That is x1, that is average of first data set is given as 29.2. x2, that is the second data set, average is given by 32.7. Sigma 1 square is given as 96.5. Sigma 2 square is given as 87.6. N1 is given. So number of data points in the first data set is given by 35, and N2 is 24. So your job is to construct a 98% confidence interval for the difference between the population means. Second, specify the competing hypothesis in order to determine whether or not the population means differ. Third one is using the confidence interval for from part A, can you reject the null hypothesis. That's a question that has been asked. Yeah. So let's see how to solve this problem. So the very first is, yeah, like we saw in the slides, 100 multiplied by 1 minus alpha confidence interval for mu1 minus mu2. Yeah. So this is your formula, which is x1 bar minus x2 bar plus or minus z at alpha by 2 multiplied by square root of sigma 1 square sigma 2 square. Yeah. So in this formula over here, x1 is given, x2 is given, sigma 1 square is given, sigma 2 square is given, n1 is given, n2 is given. Yeah. So let's see what is the unknown in this formula. So yeah, the only unknown is z at alpha by 2, right? So yeah, just like I said, x1 is this, sigma 1 is this, sigma 1 square is this, n1 is this, and x2 is this, sigma 2 square is this, n2 is this. So your confidence level at 98% is asked, right? In your question, it is asking for 98% confidence interval. Yeah. So how to interpret that is, your 100 multiplied by 1 minus alpha percentage is 98%. Yeah. So again, in this case, the only unknown is alpha. So you can rearrange, reshuffle all the entities, and that gives you your alpha value as 1 minus 0.98, which is equal to 0.02. Yeah. So now let's refer to your z table or z distribution table or your standard normal table or your standard normal curve over here. So yeah, you are looking at z alpha. So as per this formula, you are looking for z alpha by 2. Your alpha value is 0.02, which you calculated using this 1 minus 0.98 gives you 0.02. And you're supposed to look for z at alpha by 2. Yeah, so this divided by 2 gives you 0.01. Yeah. So I'm referring this z table over here. So within this z table, what I'm supposed to look at is this 0.01 number point. Where can I find this 0.01? Yeah. So suppose if I start here, everything is 0, 0, 0. I keep on moving. Well, in the very first row over here, everything is 0. Yeah. And I move 0.001. Well, again, I'm looking for 0.01. Yeah. So if I keep looking left hand side, no, nothing is 0.01. Then again, third row, nothing is near 0.01. Fourth row, nothing. Fifth row, nothing is close to 0.01. Sixth, seventh, eighth. As I'm going down and down, the numbers are increasing slightly. So again, in this row, I can see 0.001. Well, yeah, then the next, as I come down, 0.013, 0.019, 0.026, still very far away from 0.01. But as I'm going from top to bottom, the numbers are increasing, which is a good sign. So if I come here, here again, oh wow, this is the first place where I saw 0.017, right? And again, I'm looking for 0.01. So that tells me I'm supposed to look for the next row. Yeah, so the number decreased from 0.0107 to 0.0104. Next one is 0.0102. Next one is 0.0099, right? So again, I will just round it up. So this is 0.01 for me. So great news. I was looking for a number 0.01 and I found it. So now I'm looking for the actual z value for it. Yeah. So I will immediately go on my left hand side. It's telling me 2.33. Hey, well, that negative, positive, it was covered in our business stats one. Again, it's a kind of theory, but for now, I'll just skip that. I'll assume that you guys still remember it. So again, I'm looking at 0.01 over here. So I'm locating it at 2.3. And if I go vertically, it's 0.3, right? So I'll combine these two numbers and my z value is 2.33. Yeah, so 2.3 plus 0.03 gives me 2.33. So that's my z value. Yeah, so you can see my z value over here. So once I find that z value, technically I have everything that is required for me to plug into this formula over here. By that logic, my 98% confidence interval is, yeah, plug in these numbers, x1 bar, x2 bar, z, which I found over here, square root of, sigma 1 square divided by n1 plus sigma 2 square divided by n2. And I'm getting a range of negative 3.5 and plus or minus, this is what I will be getting. And when I simplify, that is negative 3.5 minus 5.9 gives me negative 9.4. Similarly, negative 3.5 plus 5.9 gives me positive 2.4. So yeah, this is the confidence interval I was looking for. So this answers my, so the first one is construct 98% confidence interval for difference between the population mean. So this is my, part A of the problem. So this is my confidence. These are my confidence intervals, negative 9.4 and 2.4. So everything is between that. Next one is specify the competing hypothesis. Yeah. So yeah, I think I have discussed this in my next slide. Yeah. Let's look at the third one. Using the confidence interval from part A, can you reject the null hypothesis? Yeah. So hey guys, like we learned in our business stats 1 in hypothesis testing, since the number 0 or the value 0 lies between this range, right? I mean, you guys agree that negative 9.4, then if you draw a line over here from negative 9.4, then 0 lies between here and then you have 2.4. So 0 lies between this range. That's why, yeah, so that's the key thing. So by that logic, the confidence interval contains 0. So the value hypothesis under the null hypothesis do not reject HO. Yeah, so that's your inference based on your inferencing techniques as per the hypothesis testing. And for part B, hypothesis test. Yeah, so how you are going to build it up. Yeah, so just remember guys, just calibrating your eyes. The three compelling cases for hypothesis tests are like either two-tailed, right-tailed or left-tailed. So it can be either mu1 minus mu2 equal to d0. That is your null hypothesis, and the contradicting is not equal to d0. Second one is less than or equal to, and third one is greater than or equal to. Yeah. So again, if I read the problem over here, consider the following data construct. Yeah, so specify the computer hypothesis in order to determine whether or not the population mean differs. Yeah. Oh, so answer is hidden over here. Population mean differs. Yeah. So by the logic, mean differs mean it can either differ yes or it won't, right? So it is telling me is the first case. So going back over here, test. Yeah. So this is your test you are trying to develop to determine whether or not the population mean differs, or like mu1 not equal to mu2, that is a two-tail. Yeah, so this is your answer, right? It's clearly saying whether it differs. So the answer could be yes or no. It is not telling me that whether the population mean can be greater than 35 or whether the population mean is less than 35 or so on. Because if in the question, if it is clearly stating greater than less than, meaning it's one tail, but here it is differs, right? Clearly it's written the word differ. That means you are only looking for equal to or not equal to. So definitely it's a two-tail test. So the null hypothesis is mu1 minus mu2 equals to 0. So if there is no difference, then the difference between these two will be 0. And by that logic, you're alternating, or your contradictory hypothesis becomes not equal to 0. Yeah. So yeah, this is your part B. And part C is, like we already discussed, 0 lies between this. That's why you are getting, we do not reject. Yeah. So that's the first problem solved. Let's look at the second problem, and yeah, I think this is your second SP case. Yeah, so this is your second condition, second scenario. So the problem states that consider the following data drawn independently from normally distributed population. Your x1 is given as this, x2 is given as this, s1 square is given as this, s2 square is given as this, n1 and n2 are given. So again, if like I clearly see, yeah, it doesn't talk about sigma. So yeah, looks like sigma 1 square and sigma 2 square are unknown. So we'll assume them to be equal, and your S1 square and S2 square are given. Yeah, so that makes our life easy. Oh, sorry, this text is shuffled, so I will recorrect it. Make it bigger. Okay, coming back. See you. So yeah, this is the given information, and here are your questions. First one is A, construct 90% confidence interval for the difference between the population means. Yeah, so again, clearly given 90%. So now you have to use that formula, right? 100 multiplied by 1 minus alpha. Yeah, so in this case, 90%. So your alpha will be 0.1. Yeah, so moving forward, assume the population variances are unknown but equal. Yeah, so it's clearly our scenario number 2. So based on that, how to calculate the confidence interval? Again, the answer is given over here, but here is a method to calculate that. So part A is your alpha is 0.1. Because here your confidence interval for is given by 90% confidence interval, right? So by that logic, your level of significance or your alpha is 0.1, which is 100 minus 90%, right? So 1 minus 0.9 gives me 0.1. So that's how your alpha is calculated. Your DFF, DFF or degrees of freedom is calculated as the like formula N1 plus N2 minus 2. Yeah. So here N1 is 28 plus N2 gives me 39 minus 2 is 37, right? So that's how you got this 37. Yeah. Then the next term is to calculate the T alpha by 2. And again, why are you calculating all these or trying to come up with all these numbers? Your goal is to plug all those numbers into this formula. X1 bar minus X2 bar plus or minus T alpha by 2 at degrees of freedom divided by square root, multiplied by square root of SP square multiplied by 1 upon N1 plus 1 upon N2. So yeah, you found your alpha over here. You found your degrees of freedom over here, which is required to get your T value. Yeah, so that's how you calculate it. Yeah, so you got your D of F here. And now let's refer to the T distribution table. So T at alpha by 2 and degrees of freedom. Yeah, so let's see the structure of the T distribution table over here. So again, this has yeah, to like a set of vertical column over here that says D of F. And again, several degrees of freedom are stated over here. 1, 2, 3, 4, 5, 6, and in this case it's 45. But again, does it have to be 45? Well, the number can go on and on. There is no limit to it. But usually, yeah, this is the right structure. So on your extreme left-hand side column is degrees of freedom, and your like horizontal row has all the different values of alpha. Yeah. So for example, here is your alpha level alpha value of 0.2, 0 0.1, 0.05, 0.025, 0.01, and 0.005. So in this case, what you are looking at is we are looking at alpha of 0.1. Yeah. So technically, yeah, so that's a 0.1. You're supposed to divide it by 2. So alpha by 2 gives me 0.1 divided by 2, which is 0.05. So I'm looking at this value over here, alpha of 0.05, which is 0.1 divided by 2. And I'm looking for a number that is at the degrees of freedom of 37. Yeah. So if I go from top to bottom, come down, I'm looking for a number 37. Here it is. So corresponding to 37 and 0.05, this is my number 1.67. Oh, sorry, 1.687. So that's my T value. So T at 0.05 and 37 degrees of freedom is 1.687. Yeah. So I got this value. So I know X1 bar, X2 bar, I found T. Now let's calculate the SP square. Yeah. So SP square, again, the formula which we already saw during the PowerPoint slide. So I just plug in those numbers. I know N1, I know S1 square, I know N2, I know S2 square, plug in these numbers and I got SP square equals to this. Now I have everything that is required. So I just plug in all these numbers into my final formula of this. I got the confidence interval of this one. Yeah. 15.5 plus or minus 1.71, which gives me, if I simplify it, my lower end is lower end of the confidence interval is 13.79 and a higher end is 17.21. Yeah. So here you go. And again, the same logic, whether or not 0 lies between these, just looking at this, hey, question for you guys, or are you guys, I want you guys to think whether or not 0 lies between these. Well, the straight answer is, well, again, this is positive, this is positive. So no, 0 doesn't lie within this. So let's go to the next slide. But again, anyways, in this slide, we solve the first one, that is identifying the confidence interval, which is this one. So that's your part A of problem 2. Next one. From part A, the interval is this. The 0 doesn't lie, it doesn't contain 0. So the value hypothesized under the under the null hypothesis, we reject HO at 10% significant levels. Yeah, so we reject the HO because 0 doesn't lie between this. Yeah. So yeah, this completes our second problem. So I want you guys to go ahead and understand all the lecture slides which are posted in our Canvas, and go ahead and start taking your quiz. Yeah, but remember, make sure you read all the lecture slides, understand them. If required, take a pen and paper. You can practice the problems. You can pull your Excel. You can practice more. And once you read, understand all the lecture slides once, read, understand second time as well. So 2 level of reading, understanding will definitely help you guys understand a lot more better. And once that's done, yeah, hey guys, give me a second. Let me pull our Canvas page for a minute. It's coming. Yeah, here you go. Yeah, perfect. So this is how your Canvas page. I will go to student view. Here is how your Canvas page is laid down. It starts with, yeah, week one course orientation information. Then there is basic R program. Anyways, your task for this week was to install R program and R Studio on your computer. That was your assignment. This week we aren't using our program, but it's coming in yeah, I think around roughly 3 weeks from now it's coming, and we'll be using yeah, I think from week 4 until last week, on and off. Then, yeah, here is the content for your lecture one. So here are the PowerPoint slides. Well, I converted into PDF. It's, yeah, file size becomes smaller. So I want you guys to read and understand twice. And once you read, understand, and practice all the problems stated on the slides, I want you guys to take this reading assignment. And again, it's one of a very basic. The reading is not a lot. I think it's only few pages. Yeah, I want you guys to read it, understand, and I think uh, the textbook will grade you based on, maybe there are some simple questions inbuilt interactive. Yeah, so this is your first assignment, 100 points. And I think in next maybe 10 minutes, I'll be posting a quiz, yeah, as well as a homework as well. So yeah, this is a sequence I want you guys to follow. Read, understand this one, then take this smart reading assignment, then take the quiz, and then yeah, finally solve your homework assignment. Yeah, and everything will be due 1 week from now, which is 3rd of September. Yeah, so you have 7 whole weeks to read, understand all, and complete the assignments. And in between, if you have any question, again, I will request all of you guys. I'm a very, very, very easy, very friendly guy. Do not hesitate to reach out to me using text or email or even MS Team message. I'll be very, very happy to help you guys. So that's it for now, guys. Thank you so much. Have a very nice day.